We will now look at spotting. Spotting can be caused by different sources: torching trees, piles of slash burning, and wind-driven surface fires. So there are different models that will use uh, will try to understand what are the processes involved with these three different types of sources. Starting by torching trees, the effect is clearly dependent on tree height, tree diameter, and also the number of trees that are burning at the same time, because they generally develop a common convection column. Also, what is the wind speed at 10 meters, and what is the vegetation height. So those are the variables that are used as inputs to try to understand what will be the distance traveled by firebrands. So the first results that we can have from those is the estimate of firebrand height. How high can a firebrand travel, and then uh, you have to translate the wind speed at a certain height to uh, the wind speed at maximum height of the firebrand. And then the output is the spotting distance, the flat terrain spotting distance. You can also have the same thing, same general mm, model that was also developed by Albini for continuous flame height of piles burning, and here the input is only the flame height itself. And so firebrand height is estimated from the flame height, and then you can have a spotting distance based on that value. And so here, for this first section, we represent what is the spotting distance and the firebrand height. And of course, the higher the firebrand can travel, the longer distance the spotting can happen. So for torching trees, you can see what happens, what is the influence of tree height. So torching trees is the darker curve. And of course, when you are going to decrease the tree height, we can press this button. So it starts with 20 meters and it goes down 18, 17. And so when it's only 1 meter, the distance will be lower. So there is a difference with tree height with models. Also, you can have a difference caused by tree diameter. So if we have a lower tree diameter, of course the heat generated will be less, and the firebrand height will be less also. And also you can have a different number of trees. You can increase, if you increase number of trees, the spotting distance will increase. If you decrease number of trees, if you have just one tree burning, it will go a little bit above 100 meters height, but it will go 1.5 kilometers of spotting distance. If you go from one tree to three trees burning at the same time, you go the spotting distance could be up to 2 kilometers. So this makes a difference. And also the difference could be because of vegetation, of wind speed. If you increase wind speed or if you decrease wind speed, you'll see that let's say firebrand height will be the same, but the spotting distance will be smaller. And vegetation height can also play a role because, as we saw before vegetation height is also controlling the wind profile. So if we have lower vegetation height, um, then the the wind is going to allow spotting to go a little bit further. Uh, and of course here it's the tree height and here it's vegetation height, because here we are talking about isolated trees that are touching. So the other thing is with pile burning. So with pile burning we can have a continuous flame height of 12 meters. Let's decrease this value from 12 to 6 meters, and then you see a very sharp decrease in both the firebrand height and in the spotting distance. And you can see what is the, say, the, the influence of flame height. And from here you can see that really when you are talking about 19 meters continuous flame height, you can have 2.5 kilometers of uh, distance traveled by firebrands. And also here you can try to play with those two curves, try to have them associated one to the other, and, and from here you see that having three trees of a certain height and a certain diameter with this wind speed is equivalent to have a pile burning with 13 meters of flame height. So it's interesting to explore a little bit these kind of relationships. The other one is quite different, is wind-driven surface fires. So here you have to start by providing fireline intensity that can be estimated by many sources, and let's talk about 50,000 kilowatts per meter. So uh, this is an important fire. So Albini also provides some intermediate results: a wind speed function, thermal strength, um, and it also provides an estimate of firebrand height. But then it decomposes the traveling distance by the firebrand between two. One is the distance traveled during lofting, when the firebrand is going up in the convection column, and so this is 0.96 kilometers. And then the second one, that is the flat terrain spotting distance. When it's there, how far does it travel? And that part of the curve is quite similar to that one. And then the total spotting distance he computes as the sum of the two. So 0.96 during lofting, 1.65 during descent, and the total is 2.61 kilometers for this very intense uh, fire. So this is basically the approaches that are used in many of the softwares that are available to predict spotting distance, and it's it's good that you can compare them, that you have in the same spreadsheet the possibility of looking at both, looking at the estimates, and understand how they operate, the inputs, the outputs, and the intermediate results. So the plan is to work with the spreadsheet and try to have a feeling for the important variables to that determine the spotting distance, knowing that spotting distance is a very important characteristics that affects very much the firefighting strategies.